Here's a project that a friend of ours was working on a year ago, a super compact personal VTOL aircraft, in which he encountered a problem that is very common to not just aircraft, but engineering design as a whole. You start your design with initial weight targets. Then, you begin iterations between customer needs, aerodynamics, structure, safety, performance and more. At some point, you often discover that you have exceeded your initial weight assumption, even if only a few percent. When this happens, it shouldn't be taken lightly. Because as a minimum, you'd have to redo a lot of your calculations, and maybe even make design changes, in order to accommodate the extra weight. And if you already have a customer, you'd be defaulting on the specs that you promised. Either way, everyone would be happy if you could find a way to meet your initial weight targets. This is a common situation in product design, especially in large companies, where products gain weight during their detail design. So and extra weight must be shed off, or the product will not meet its promised specifications. Here's this personal aircraft that this friend is working on. He shared with us the weights update on the right, which was done relatively late in the design process, and after all the calculations at the back were already performed. This update revealed that the initial weight target was missed by 28 pounds. Looking for ways to save weight and return to the original target, this guy made a list, and indeed, there are means by which weight can be saved in each of the vehicle's weight groups. Next to each weight-saving idea is also the estimated cost of implementing it. Which combination should this guy go for? Trying all the possibilities is a no-go, as we can see at the bottom of the screen, so we suggested to use genetic algorithms. Here's our problem statement: we need to pick items from the list, to achieve a target delta weight equal or greater than 28 pounds, all at minimum cost. Remember that a chromosome is also a candidate solution. Here, we will use a binary representation, using a 0 next to an item that will not be picked, and a 1 if it is to be included. Not having a predefined idea how the list will look, we will start with a random collection of 1s and 0s for our first chromosome. The fitness function here is simply minimum cost. We also have a hard constraint, which is that the sum of the items in the list must be higher or equal to 28 pounds. So let's start. Running our genetic algorithm code written in Python, the progress of the run is visible on the left. The vertical axis shows the fitness, and the horizontal axis is the current generation number. And here are the chosen items, printed at the end of the run to the right of the graph. As we can see, the not under 28 pounds constraint was met. Notice that the run started with a fitness, or cost, of $900, which is what the program calculated for the first, randomly generated individuals. Then it started improving, stopping at around $390, the lowest cost it could get to achieve 28 pounds. The run stopped after 30 generations, with no significant further improvement to the fitness. Note that fluctuations in the run continue even after reaching the level of 390. This is characteristic of many genetic algorithm runs. Why is that, you may ask? Look around you, are all humans identical? Is there anything living under the sun that is an exact copy of another? Getting back to our problem, let's also add that a different problem to solve would have been, how much weight can we save, if we have just $200 to spend on this effort? In such event the constraint and fitness function would switch places, but other than that, it would look very similar to this run. So to summarize, this example demonstrated just one way by which genetic algorithms stand alongside the engineers, providing them with guidance on difficult to solve problems. The same would apply to managers, doctors and people in many other professions. Again, no other AI tool can solve these type of problems, let alone provide such valuable input to the designers, and with so little effort on their part. And remember, genetic algorithms can solve problems for systems and products that have thousands and even millions of parts. We shall see more of that in other genetic algorithms examples on this channel.